Watching the previous video will give you a good understanding of how to use tree diagrams to represent probabilities similar to the questions present in this video. The focus in the last video was the probability of repeated events, such as the same bag of marbles or the same person's probability. In this video, we focus on when there are separate, independent events and the probabilities that can be found from them. Pause and have a look at this question. We set up our tree diagrams by showing the branch of each Emeka or Kunle's probabilities first. I'll start with Emeka. Emeka either has racing games or doesn't have racing games. The other types of games are not the concern, as the question does not ask about them. The probability Emeka selects a racing game is 7 games out of 10, or 7/10. Therefore, the probability Emeka selects a non-racing game is 3 out of 10. To check that this is right, 7/10 plus 3/10 must equal to a whole or 1, which it does. For Kunle's probabilities, they will branch off of Emeka's. The probability Kunle selects a racing game is 5 out of the total number of games he has, which is 5 plus 3, which equals to 8. So, therefore, the probability is 5 out of 8. Therefore, the probability of not selecting a racing game would be 3 out of 8. Adding both still gives a whole. Now our tree diagram is set up, we can answer the questions. The probability of Emeka selecting a racing game and Kunle selecting a non-racing game is 7 out of 10 times by 3 out of 10, which equals to 21 out of 80. The probability both select a game that isn't a racing game is 3 out of 10 times by 3 out of 8, which equals to 9 out of 80. The probability only one of them selects a racing game is 7 out of 10 times by 3 out of 8, plus 3 out of 10 plus 5 out of 8, as both pathways have one of them selecting a racing game. Since both paths match the criteria, they are both added together. 7/10 multiplied by 3/8 equals to 21/80. 3/10 times by 5/8 equals to 15/80. Then finally we add these two together. 21/80 plus 15/80 equals to 36/80. This is the final probability. You can simplify if you want, but it isn't necessary if the question doesn't ask. However, simplifying won't lead to a loss of marks. Simplified, the answer is 9 out of 20. Pause and have a go at this question. As we know, each branch adds up to 1, so to find the missing values, we subtract the probabilities from 1. 1 minus 0.7 equals to 0.3. The probability she fails maths is 0.3. 1 subtract 0.55 equals to 0.45. The probability she passes English is 0.45. Now, we filled in the tree diagram. The probability she passes both tests is 0.7 multiplied by 0.45, which equals to 0.315. The probability she passes at least one of her tests is a combination of all the paths that show at least one pass. Pass, pass fail, and fail pass. Now, like before, we could calculate each pathway and then add the probabilities together, like we've been doing, and this will give us the final answer. However, this could be a lot of calculations. Let's use what we know about the end probabilities of each outcome. Calculating the probabilities of each 4 pathways gives us these answers. If we add these 4 numbers together, what would be the sum? The sum will always equal to 1, or a whole. Looking at what we know, 3 out of the 4 pathways are going to be added together to give us the final answer. The final probability out of the 4 is left out of the calculation. Wouldn't it be easier to calculate the probability that isn't part of the final answer and subtract that probability from a whole or 1? Let's try both. After calculating for each outcome, adding these 3 gives us 0.835. Let's instead use the probability that isn't part of the final answer, fail, which is 0.165. Subtracting 0.165 from 1 gives us 0.835, the same answer. Comparing, there are less steps to calculating the answer, but are both viable techniques. To summarize, tree diagrams can be used to find the probability of outcomes of different events. If all the pathways except for 1 are valid, subtracting the probability of that single outcome from 1 gives the probability of the sum of the other outcomes.